For a while, TRAPPIST-1 felt like the closest thing astronomy had to a shortcut. 7 Earth-sized planets around one nearby star, several in the so-called habitable zone. A system compact enough for repeated observation and strange enough to keep hope alive. It was easy to hear that description and quietly replace every unknown with something familiar. Oceans, weather, air, maybe even life. But the closer James Webb has looked, the less this system resembles a row of alternate Earths, and the more it begins to look like a kind of trial by fire, a place where rocky worlds are tested, stripped, and forced to reveal what they actually are. That is what makes Webb's verdict so important. It is not a single dramatic yes or no. It is harsher than that and more valuable. It is the slow collapse of easy optimism. It is the difference between a planet and a world becoming impossible to ignore. If you enjoy long, careful journeys through realities like this, stay with me. There is a lot to see here, and the deeper we go, the stranger and more honest this system becomes. So let's begin somewhere simple, with a misconception almost all of us are vulnerable to. When people hear the phrase Earth-sized planet, what they often picture is not just size. They picture familiarity. They picture ground underfoot, a horizon, a sky that behaves more or less the way a sky should, and an atmosphere doing its quiet, invisible work. They imagine a world already halfway toward being livable. It is an understandable mistake, because size feels intimate. A gas giant is obviously alien. A rocky planet about as large as Earth feels emotionally closer, as though the universe has already met us halfway. But size is one of the easiest planetary traits to overvalue. A world can be almost exactly Earth's width, and still be unrecognizable where it matters most. The rock can be there, the gravity can be close, even the amount of starlight can sound promising on paper, and still the place itself can be dead in the ways that count. No stable air, no ocean, no chemistry cycling in a long, patient rhythm. Just surface extremes, radiation, and a silence too complete to soften. That is the real subject here, not whether TRAPPIST-1 contains Earth-sized planets. We already knew that. The question is whether any of them became worlds in the full sense of the word, whether any of them managed to hold on to the fragile, thin envelope that turns stone into climate, climate into chemistry, and chemistry into possibility. Because an atmosphere is not just air. It is a planet's skin, its blanket, its memory. It stores heat, moves energy, filters violence, and lets one region of a world talk to another. Remove it, and the surface stops behaving like a connected place. Day and night pull apart. Temperatures become less like weather and more like opposing fates. The world does not just become harsher, it becomes broken into separate physical realities. And around TRAPPIST-1, that matters immediately. The star itself is not sun-like in the way most people imagine stars to be. It is an ultra-cool red dwarf, tiny and dim by stellar standards, so small that if you placed it beside our sun, the comparison would feel less like two versions of the same thing, and more like a lantern beside a furnace. That dimness is part of what made the system so exciting in the first place. A smaller star is easier for a small planet to cross. When one of these worlds passes in front of TRAPPIST-1, the dip in starlight is relatively large, and that makes the system unusually good for measurement. In other words, the star made these planets visible, but the same fact that helps us observe them also changes everything about how they live. Because a dim star has to be orbited closely if a planet is going to receive anything like temperate levels of energy, and the TRAPPIST-1 planets are close, very close. Their entire system is packed into a region where, by the standards of our own solar system, Mercury would already feel uncomfortably near the Sun. Imagine taking the broad architecture of planets and compressing it until the whole arrangement fits into a space that, to us, hardly feels like a full system at all. That is TRAPPIST-1. A year there is not a long, slow sweep through seasons. It is days, sometimes just a few of them. That compression does something else. It makes tidal locking likely. And tidal locking is one of those ideas that sounds technical until you actually picture it. A tidally locked planet does not spin under a moving day like Earth does. One side faces the star endlessly. One side faces away. Permanent noon, permanent night. If you stood on such a world, sunrise would not be something you wake up to. It would be a geographical direction. Light would be a place. Right away you can feel how much depends on the atmosphere. On Earth, air and oceans move heat around the globe so efficiently that no one place has to survive entirely on its own. The tropics influence the poles. The oceans feed the sky. Winds carry memory from one hemisphere to another. But on a tidally locked planet with little or no atmosphere, the day side can become a region of relentless heating, while the night side sinks toward brutal cold. Not a world with climates, a world divided into them. This is why the phrase habitable zone, useful as it is, can mislead people. It sounds more generous than it really is. The habitable zone is not a verdict. It is not a promise. It is just the rough region around a star where liquid water could exist on a surface under the right conditions. Under the right conditions. Those words do almost all the work. You still need the planet to keep an atmosphere. You still need temperatures moderated, chemistry sustained, surface pressure plausible, and stellar violence not so intense that whatever the planet manages to build gets torn away faster than it can recover. So even before Webb gave us new data, the central question around TRAPPIST-1 was never simply distance from the star. It was survival. Could these planets hold on to their air? That is where the old dream begins to narrow. James Webb is not looking at TRAPPIST-1 the way most people imagine a telescope looking at something. It is not sending back a dramatic portrait of blue oceans or cloud bands curling over continents. At this distance, nothing like that is available. What Webb is doing is far stranger, and in some ways more impressive. It is measuring tiny changes in starlight as these planets pass in front of their star, or move around it, trying to infer whether a thin layer of gas surrounds a piece of rock 40 light-years away. It is less like photography than forensics. Or listening. Imagine trying to tell whether someone across a vast, dark valley took a single breath, not by seeing their chest rise, but by noticing the faintest change in the sound of wind passing a distant gate. That is closer to the spirit of what is happening here. Webb is trying to hear atmospheres through light, and the more carefully it listens, the more severe the system becomes. Because once you understand that atmospheres are the real battleground, the inner planets stop looking like exciting candidates and start looking like evidence. Not evidence of life, but evidence of loss. Evidence of what happens when a rocky planet lives too close to a small star for too long and fails to keep the one thing that could have made it more than stone. TRAPPIST-1b is where that harder picture begins. Not as a maybe, as a warning. TRAPPIST-1b circles its star so closely that the scale almost slips past intuition. In our own solar system, distance gives us emotional cues. Mercury feels close because we have learned to think of it that way. Venus feels dangerous. Earth feels safe. But TRAPPIST-1 rearranges those instincts. Its innermost planet is pressed so near its star that a year there lasts barely more than a day and a half by our standards. Time itself seems compressed, as if the whole orbital logic of a solar system has been wound tight. For a while there was room to imagine that even a world like this might still have something substantial wrapped around it. A thick atmosphere can change everything. It can reflect light, trap heat, circulate energy, and create the kind of planetary continuity a bare rock never gets to have. If TRAPPIST-1b had been swaddled in dense air, then the story would not have been comfortable, but it would still have been physically interesting in a more open-ended way. It might have been a kind of super Venus, harsh but dynamic, a world with weather of a sort, chemistry of a sort, maybe cloud decks rising over a furnace of stone. Webb has made that gentler speculation much harder to keep. When the telescope measured the thermal glow from the day side of TRAPPIST-1b, what emerged was not the signature of a thick, insulating atmosphere redistributing heat around the globe. It looked much more like a surface directly exposed, taking the star's energy on one face and shedding it back into space with very little mediation. The kind of behaviour you expect from a bare rock or something close to it. A planet whose star-facing side becomes intensely hot because there is almost nothing there to soften the blow or share the burden. That is an important shift in tone. We are no longer asking only what kinds of exotic atmospheres these worlds might have. We are now confronting the possibility that some of them may not have atmospheres worth speaking of at all. If you were somehow able to stand on the day side of TRAPPIST 1b, nothing about the scene would resemble the generous planetary imagination people often bring to exoplanets. There would be no moving weather to make the place feel alive, no familiar sky thick with suspended blue, no slow negotiation between light and air. Instead, you would have direct stellar force bearing down on rock. Permanent day, permanent heating. The star above would hang in the same place. Larger in the sky than our sun appears from Earth, its red-orange light fixed and unwavering. Not a sunrise, not a day, a condition. And on the far side, beyond the reach of any meaningful heat transport, the opposite reality waits. That is what an atmosphere prevents. Without one, a tidally locked planet is not merely extreme, it is physically disunified, almost as though the two hemispheres belong to different worlds that happen to share the same core. TRAPPIST 1c deepens that picture rather than interrupting it. This matters because one stripped world could always be written off as an edge case. Too close, too unlucky, too singular to support a larger conclusion. But the next planet out begins to suggest pattern. TRAPPIST 1c receives less punishment than B, yet Webb's observations have also pushed against the idea that it carries a thick atmosphere, especially the sort of carbon dioxide heavy envelope that would have made it easier to detect. More recent work has made the case harsher still. Whatever C is, it does not appear to be hiding under the kind of substantial gaseous cover that earlier hopes could comfortably project onto it. That changes the emotional geometry of the whole system, because at that point we are not just crossing off planets, we are learning something about atmospheric survival close to this star. Two neighbouring rocky worlds, both roughly Earth-sized, both apparently poor at keeping or rebuilding the kind of substantial air that turns surface conditions into something more connected and more forgiving. The dream is no longer being challenged by one world, it is being narrowed by a trend. This is where Webb's verdict starts to feel less like a collection of measurements and more like a line of case files. Each planet adds not just information about itself, but pressure on the interpretation of the next one out. It is a little like walking through the rooms of an abandoned house and noticing the same kind of damage repeating in place after place. By the time you reach the third room, you are no longer asking whether something happened, you are asking what kind of force passed through the entire structure. That force, here, leads us back to the star. Red dwarfs are often described as promising targets in the search for life, because they are common, long-lived, and observationally convenient. All of that is true, but there is another side to that truth, and TRAPPIST 1 keeps dragging us toward it. A red dwarf's gift for easy measurement is tied to a style of planetary life that can be brutally difficult. These stars are smaller and cooler than the Sun, yet they can be magnetically active in ways that matter enormously for nearby planets. Their flares, their ultraviolet output, the charged particles flowing outward from them, all of it becomes more consequential when a planet is orbiting at such intimate range. To understand why, it helps to stop thinking of space as empty calm. Around a star, it is not. A planet lives inside a moving environment of radiation, particles, and magnetic stress. Here on Earth, our atmosphere and magnetic field work together as a kind of layered defense. Most days we do not feel that protection happening, which is exactly what makes it so easy to undervalue. We live below a sky that looks passive, when in fact it is shielding us from a star that would otherwise sculpt the planet more aggressively than daily life suggests. Around TRAPPIST 1, the shielding question becomes central. If a world begins with a light, primordial atmosphere rich in hydrogen and helium, that atmosphere is vulnerable. It can be stripped away. That part is not especially surprising. The harder question is what comes after. Can the planet build a second atmosphere from volcanic outgassing and internal chemistry? Can it regrow lungs after losing the first pair? Can it hold on to heavier gases long enough for climate to stabilize? Can it do all of that while orbiting in a region where the star remains not distant weather, but an immediate presence? The inner planets are starting to imply how difficult that may be. And difficulty here does not just mean heat, it means history. A world can be in a relatively favourable place now and still be haunted by what happened early. Red dwarfs may live for extraordinary spans of time, vastly longer than stars like our Sun, but their youth can be violent and prolonged. For planets close in, that youth matters. An atmosphere does not merely have to exist at the moment we observe it, it has to survive a gauntlet, or be rebuilt after one. That is part of what makes TRAPPIST-1 so compelling now. We are no longer looking at a simple lineup of maybe habitable planets. We are looking at the aftermath of a long atmospheric struggle, which is why the next world matters so much. Because when we move outward from B and C, we are not just moving to another planet. We are moving to a test of whether the pattern continues, or whether somewhere in this compressed architecture, a world managed to hold the line just long enough to become more than exposed stone. TRAPPIST-1d sits in exactly the kind of narrative position that tempts people into hope. It is farther out than the first two scorched suspects, closer to the region where liquid water can at least be discussed without sounding absurd, and for years it occupied that vague but powerful category of worlds people wanted to keep emotionally open. Not confirmed, not safe, just available for projection. A rocky planet at the inner edge of the habitable conversation, small enough to feel tangible, distant enough from the star to seem less obviously doomed. That emotional opening has narrowed too. Webb's measurements have not given TRAPPIST-1d the kind of atmosphere people were waiting for. Not an Earth-like one. Not the kind that would make the planet feel climatically balanced, chemically rich, and comfortably survivable in any straightforward sense. That does not mean every possible atmospheric scenario is dead. It does mean one of the easiest and most reassuring stories about the planet has started to fail. And that matters, because by the time the third inner world begins to look difficult, it becomes harder to keep telling yourself that the system is mostly fine, mostly promising, mostly just waiting for confirmation. Something more severe is taking shape. This is where the meaning of Webb's verdict becomes clearer. The telescope is not merely identifying the best candidate, it is teaching us how to stop confusing geometric promise with lived planetary reality. A system can be full of rocky bodies in favourable orbital positions and still be deeply inhospitable. The usual language people reach for in exoplanet headlines begins to feel too soft here. Earth-sized, temperate, in the habitable zone. Those phrases are useful, but they are also dangerous if you let them work on your imagination unchecked. They describe possibilities at a distance. They do not describe what it would feel like to stand there. And feeling that distinction is important. Imagine a world where there is enough incoming energy, in principle, for surface water somewhere, but not enough atmospheric structure to spread heat, buffer extremes, and protect complexity. The result is not a mild near Earth. It is a place where the map itself becomes destiny. Too close to the fixed star, and the surface may bake. Too far into permanent dark, and volatiles can freeze out, or conditions collapse into sterility. What remains, if anything remains, is a narrow borderland between those extremes, a band of perpetual twilight where the star never rises and never sets, where habitability is not a global trait, but a fragile strip of compromise. That idea, sometimes called Terminator habitability, is one of the most haunting possibilities in systems like this. Not because it is romantic, but because it forces us to think more carefully about what survival might actually look like on a tidally locked planet. Life, if it existed in such a place, might not inherit a whole world. It might inherit a seam. That alone should change how the system feels in the mind. These are not just planets lined up around a small star. They are potential climates pinned to geometry, their prospects determined by whether rock, air, water, and stellar violence ever reached something like a working arrangement. When that arrangement fails, the loss is not abstract. A whole planetary future closes, and with B, C, and now D becoming harder to imagine as easy successes, the system starts behaving less like a cosmic invitation and more like a lesson in how often rocky planets may fall short of becoming true worlds. Yet that lesson is not purely negative. In science, elimination is not disappointment when it sharpens the real question. If anything, it is relief. The fog thins. Possibilities that once sprawled everywhere begin to contract into the few that matter. Webb is not taking wonder away from TRAPPIST-1, it is concentrating it. To feel how dramatic that concentration is, it helps to zoom out from the individual planets and look again at the star they share. TRAPPIST-1 is small and cool enough that all 7 planets huddle close. Its light is redder than sunlight, its warmth weaker, its physical size modest by stellar standards. But small does not mean gentle, not here. Around stars like this, proximity is destiny. The same closeness that lets Webb detect exquisite signals also means these planets live under a kind of sustained intimacy with their star that Earth never has to endure. Here, even the sky would feel different in a way that goes beyond colour. On a suitable dayside in the TRAPPIST-1 system, the star would loom larger than our Sun appears from Earth. Not blinding white, but a deeper red-orange disk fixed overhead, as though the universe had chosen one late permanent hour and refused to move on from it. That image has a strange beauty to it, a stillness, a perpetual sunset logic. But beauty is not safety. The same star filling more of the sky also means the planet is living inside a far more immediate stellar relationship. Any flare, any magnetic agitation, any burst of high-energy output becomes harder to ignore, because there is so little distance to absorb it. This is one of the central paradoxes of red dwarf systems. They look favourable in spreadsheets. Long stellar lifetimes, abundant throughout the galaxy, small stars that make small planets easier to find. But planetary habitability is not a spreadsheet problem alone. It is a history problem, a survival problem. A matter of whether a world got through its star's worst phases, with enough of itself intact to begin the slower work of becoming complex. That early history may be where many hopes quietly die. Because a young red dwarf can spend an extraordinarily long time in a more active state, longer than many people intuit. The star's chaotic youth can stretch out, and for planets packed nearby, that can mean long exposure to intense radiation and particle bombardment during the exact era when atmospheres are being lost, rebuilt, or chemically transformed. A rocky planet may start with one atmospheric makeup, lose it, attempt another, and lose that too. Or it may outgas heavier molecules from its interior, only to find that the star is still not finished stripping them away. By the time the star settles into a calmer maturity, some planets may simply be spent. That is the hidden cruelty in the phrase long-lived star. Longevity sounds like opportunity, and eventually it can be, but it may come after an almost absurdly long, dangerous childhood. Deep time is not automatically a gift if the early terms are brutal enough. This is why the inner planets matter so much beyond themselves. They may be showing us what prolonged exposure near a red dwarf actually does. Not in theory, in a real system. Not with broad demographic statistics across thousands of exoplanets, but with individual worlds close enough and cooperative enough in their transits for us to interrogate directly. They are evidence left behind after a stellar upbringing we can only partially reconstruct. Seen that way, TRAPPIST-1b, C and D begin to feel almost forensic. They are less like failed versions of Earth and more like damaged records of a deeper environmental truth. Each one says something about atmospheric fragility. Each one narrows what we can reasonably expect farther out. Each one turns the system into a sequence of verdicts rather than a row of fantasies. And when a system starts delivering verdicts, one planet inevitably begins to draw the weight of everything. Not because it is guaranteed to be habitable. Not because it has been confirmed as blue, wet, and breathing. Quite the opposite. It matters because it has survived the culling in our minds. It remains standing after the easy analogies have started to collapse. It is the world whose uncertainty still has structure. That world is TRAPPIST-1e. By the time we arrive there, the mood should be different from the one people brought to this system years ago. We should not be arriving as tourists hunting a backup Earth. We should be arriving as witnesses who have already seen what this star can do to a rocky planet. We should feel the pressure of the prior worlds behind us. We should understand that the question is no longer whether TRAPPIST-1 contains vaguely promising planets. The question is whether one of them, just one, managed to thread the needle. And if one did, it would not make the rest of the system less important. It would make them more so. Because then the contrast between ruined worlds and surviving world would tell us something profound about how narrow the path may be. TRAPPIST-1e sits close to the middle of that path, like a coin balanced on edge between ocean and stone, between atmosphere and exposure, between a world that can carry climate and one that never quite became more than rock under a fixed star. That is why TRAPPIST-1e does not feel exciting in the same way the whole system once did. The system used to inspire a kind of wide, generous hope. 7 Earth-sized planets, several in the habitable zone, a nearby red dwarf small enough for careful study. The imagination could spread itself across the lineup and stay comfortably vague. TRAPPIST-1e is different. Its importance is narrower, more disciplined, and in some ways more intense. It matters because the room for self-deception is smaller there. This planet sits in the star's habitable zone, in the most scientifically serious sense available in the system. Not because the phrase habitable zone has suddenly become magical, but because if a world around TRAPPIST-1 were going to hold surface liquid water under something like familiar pressures, this is the place where the possibility remains most defensible. It is close enough to receive useful energy, far enough to avoid the worst of the inner furnace logic, and dense and rocky enough to belong in the category we care about. Not an ice giant, not a gas dwarf, a rocky world that still has a case. Even so, by the time Webb turned its attention there, the tone had already changed. Astronomers were no longer simply asking whether TRAPPIST-1e might be temperate. They were asking a harder question. What kind of atmosphere, if any, could have survived here after everything the star likely did to it early on? And if something survived, would it resemble anything easy to name? That last part matters more than it may seem. One of the quiet ways people mislead themselves in planetary science is by reaching too quickly for familiar analogies. Earth-like, Venus-like, Mars-like. Those comparisons are useful as first handles, but they can become traps. They encourage the mind to sort a truly alien world into pre-existing bins before the evidence has earned that simplicity. Webb's measurements on TRAPPIST-1e have been valuable partly because they have made several of those easy bins less convincing. A light, primordial atmosphere dominated by hydrogen and helium does not fit the data well. That is already telling. It means the planet probably did not simply retain the gaseous leftovers of its birth. Those light gases were likely lost long ago, stripped away or otherwise dispersed. In one sense, that sounds severe, and it is. In another sense, it is what you would expect if the planet was ever going to become interesting to us in a more Earth-comparable way. A hydrogen-helium shroud is not the atmosphere of a rocky surface world in the sense we usually mean. Losing that first envelope is part of the long road towards something more chemically mature. But then the obvious alternatives begin to fail too. A very thick carbon dioxide-heavy atmosphere, the kind that would make TRAPPIST-1e a clearer cousin to Venus, is not favoured either. Nor does the simple image of a thin, Mars-like atmosphere settle the problem cleanly. That leaves the planet in a scientifically rich but emotionally difficult place. The easy stories are thinning out. We are left with narrower, more conditional possibilities, and those possibilities are where the real tension begins. Because once the familiar analogies weaken, you have to think in terms of processes rather than labels. Could TRAPPIST-1e possess a secondary atmosphere built from heavier gases released over time by volcanic outgassing and interior chemistry? That is one plausible path. If so, the atmosphere might be dominated by nitrogen or other heavier molecules, with smaller but crucial contributions from carbon dioxide, water vapour, methane, or some combination that controls greenhouse behaviour in a much more delicate balance than the word habitable usually implies. Such an atmosphere would not merely sit above the planet. It would decide whether heat reaches the night side, whether water stays mobile, whether surface pressure allows stability, whether a global ocean is possible, and whether the planet acts like one connected body instead of two opposing hemispheres. That is a lot to ask of a thin layer of gas around a distant rock. And yet that is the layer Webb is trying to read. It helps to pause and feel how improbable this act of measurement really is. We are not looking at continents. We are not seeing weather systems turn. We are not zooming in on cloud breaks above a sea. What we have are tiny changes in starlight passing through or around the edge of a planet during transits, along with thermal clues drawn from how the world absorbs and re-radiates energy. From that, astronomers attempt to distinguish among atmospheric scenarios whose differences can be subtle even in theory. It is like inferring the architecture of a house by the way a curtain stirs in another city. The achievement is already astonishing before the answer is known, which makes the uncertainty around TRAPPIST-1me more compelling, not less. Because uncertainty here is not emptiness, it is structure. We know enough to rule out some paths. We know enough to say the planet is not simply one of several interchangeable, maybe Earths. We know enough to understand that its climate, if it has a working climate, would likely be shaped by tidal locking, atmospheric transport, and stellar history in ways that make the Earth comparison feel almost too generous. And we know enough to sense how close the planet may lie to failure. Picture the day side again, but this time not as a bare furnace like the harshest picture for the innermost planet. Imagine instead a world where the star still hangs fixed in the sky, red, orange and enlarged, but where an atmosphere exists substantial enough to move heat away from that eternal noon. Winds rise, temperature gradients soften. Perhaps clouds form more readily in some regions than others. Perhaps the hottest point does not sit directly beneath the star, because atmospheric circulation drags energy elsewhere. On the dark side, temperatures may still plunge, but not so completely that every volatile freezes beyond recovery. The two hemispheres begin to communicate. The world acquires continuity. That continuity is everything. Without it, habitability becomes a small accident of geography. With it, the possibility of a true climate appears. Not comfort, not paradise. A climate. A system. Something dynamic enough for chemistry to accumulate consequences over time. Now reverse that picture only slightly. Suppose the atmosphere is too thin, too patchy, or too compositionally strange to move enough heat. Then the day side and night side pull apart again. Liquid water, if it exists at all, may survive only in restricted zones. Perhaps there is a narrow region of twilight where conditions moderate into possibility, a permanent ring of low-angle light circling the globe. Perhaps surface water cannot persist broadly, but subsurface reservoirs remain hidden below ice or rock. Perhaps methane high in the atmosphere interacts with the star's redder output in a way that cools the surface more than our Earth-trained intuitions would expect. The range of options becomes alien very quickly, and this is why Webb's verdict on TRAPPIST-1e feels so charged. Not because it has settled the question, but because it has moved the planet out of fantasy and into a hard, narrow corridor of real scenarios. Some hopeful, some bleak, none simple. There is something almost courtroom-like about it. The wildest claims have been dismissed. The easiest acquittals have also been denied. What remains is the case itself, stripped of theatre. Evidence still being weighed, interpretation still under pressure. A planet whose future in our imagination now depends on a few atmospheric possibilities that are both subtle and consequential. And all of that would already be enough. A world 40 light-years away, its climate hanging on the interpretation of faint light. But TRAPPIST-1 does not make things that easy, because the star is not merely the source of illumination in this investigation. It is interference too. The closer we get to asking whether TRAPPIST-1e has a real atmosphere, the more we run into the maddening fact that the star itself can imitate, obscure, or distort the very signals we are trying to read. So even here, at the system's most serious candidate, we are not just studying a planet. We are trying to judge the colour of fog while the lamp behind it keeps flickering. That flickering is not a minor annoyance. It sits near the heart of the entire problem. When we talk about reading an exoplanet atmosphere, what we are really talking about is contrast. A planet passes in front of its star, and a tiny fraction of the starlight interacts with whatever gases may be sitting at the planet's edge. Certain wavelengths are absorbed a little more than others. Tiny patterns appear. From those patterns we try to infer composition, thickness, temperature structure, and sometimes pressure. It is an almost absurdly delicate method, which means anything strange in the star's own light can contaminate the result. TRAPPIST-1 is exactly the kind of star that refuses to stay politely in the background. Its surface is not a perfect, stable lamp. It can have spots, bright regions, magnetic activity, subtle changes in output, and a spectral personality of its own that complicates the work of separating planet from star. If the star's light shifts in the wrong way at the wrong time, a feature that seems to belong to the planet may partly belong to the star instead. A molecule hinted at in the data may be less a discovery than a question. A missing signal may not mean absence. It may mean interference. This makes the atmosphere of TRAPPIST-1 harder to interpret in a way that is both frustrating and profound. We do not simply need a better planet signal. We need to understand the star well enough to stop it from impersonating the evidence. That is such a strange place for the search to arrive. The Great Telescope is pointed toward one of the most famous systems in modern astronomy, and the bottleneck is not just the smallness of the planet or the thinness of its possible air. It is the fact that the star itself keeps getting in the way. Webb is not only trying to detect a whisper, it is trying to decide whether the room itself is whispering back. And yet even that difficulty gives us something valuable. It reminds us that planets do not exist as isolated objects waiting to be classified. They are embedded in stellar relationships. They are products of long exposure, long bombardment, long compromise. If the star is hard to subtract from the measurement, that is fitting in a deeper sense, because the star is also hard to subtract from the planet's history. TRAPPIST-1e is whatever it is because of that star. Its chemistry, its losses, its climate possibilities, its entire road toward or away from habitability. All of it runs through the red dwarf above it. Which brings us to one of the most unsettling things about red dwarf systems. The very stars that seem to promise almost endless time for life may spend such a long early period making life difficult that the time arrives too late. Our sun is powerful, but in the language of stellar history, it is a relatively ordinary middle-aged star with a finite future. Red dwarfs are different. They can persist for durations so long they almost resist emotional comprehension. Trillions of years in some cases. The mind hears numbers like that and tries to translate them into abundance. More time for planets to cool. More time for chemistry to organize. More time for life to emerge, adapt, and perhaps flourish. But a long life is not the same as a gentle upbringing. Small stars can spend extended periods being far more unruly in their youth than the calm image of a dim red ember suggests. During those eras, the radiation environment around close orbiting planets can be intense. Ultraviolet and X-ray output can run high, flares can be frequent, stellar winds can be punishing. If a rocky world is close enough to eventually sit in the habitable zone of a mature red dwarf, then it is also close enough to endure the worst of that early activity up close. That is the trade. Favourable distance later may mean dangerous distance early. So when we ask whether TRAPPIST-1e has an atmosphere now, we are really asking a layered question. Did the planet lose its primordial gases? Probably. Did it later build a heavier secondary atmosphere? Maybe. Did the star then strip that away too? Possibly. Did volcanic outgassing, interior heat, magnetic shielding, or sheer planetary resilience allow some version of a stable atmosphere to persist anyway? That is the narrowing frontier, and somewhere inside that frontier lies one of the most beautiful and merciless truths in planetary science. A habitable world is not produced by one good trait. It is produced by surviving a sequence. You need the right kind of planet, the right mass, the right composition, the right distance at the right time, the right atmospheric evolution, enough internal activity to renew what is lost, but not so much chaos that climate never settles, enough shielding to survive stellar aggression, enough water, but not in forms or places that make a surface permanently hostile, enough stability for chemistry to stop resetting itself and start accumulating consequence. Miss too many of those gates and the world remains a planet, but not the kind that can carry a biosphere. That is why the case of TRAPPIST-1e has such force. It sits in our awareness like an unfinished sentence, not because we know so little, but because we know enough to understand what is at stake. If E turns out to have no meaningful atmosphere, then one of the most promising habitable zone rocky planets around a nearby star will have joined the harsher pattern already suggested by its inner siblings. If it does have a secondary atmosphere, then we have something even more valuable than a pleasant headline. We have proof that at least some rocky worlds around active red dwarfs can make it through the gauntlet. Either way, the result matters far beyond one planet. Because TRAPPIST-1 is becoming less like a celebrity system and more like a laboratory, a place where we are no longer simply counting planets in habitable zones, but testing which kinds of worlds survive around the most common stars in the galaxy. If the inner planets are mostly stripped, and E stands as a borderline survivor or near survivor, then that is not just a local story. It changes the statistical mood of the search for life. It tells us that the galaxy's most common stars may offer vast numbers of rocky planets, but not necessarily vast numbers of stable surface worlds. That distinction could reshape expectations for decades. For a long time, abundance itself carried emotional weight. There are so many red dwarfs, so many rocky planets, so many habitable zones. The numbers invited optimism almost automatically. But abundance at the level of raw planets is not abundance at the level of lived environments. A street full of houses tells you nothing about how many still have working roofs, and Webb, quietly, methodically, has begun checking the roofs. That is one reason the inner planets feel so important. They are not dead ends in the story. They are calibration. They teach us what failure looks like under this star. They show us what becomes of worlds that either never kept substantial air or could not hold on to it for long enough to matter. They let us stop romanticizing mere rock. They force us to respect atmosphere as the difference maker it has always been. Which also means they sharpen the emotional pressure around the outer planets, even though those worlds are harder to read. Because farther from the star, the logic changes again. Less heating, less obvious surface thermal contrast, different climate possibilities, weaker signals for Webb to interpret, more room perhaps for water to survive in some form, but also more ambiguity, more cold, more scenarios in which oceans might exist beneath ice or atmospheres might behave in unfamiliar ways. The system does not become simpler as you move outward, it becomes murkier. And that murk has a purpose in the story. After the severe clarity of B, C and D, the outer planets remind us that ignorance is not distributed evenly. Some worlds are easier to rule out than to understand. Some are harsh enough to expose themselves quickly. Others retreat into colder uncertainty. TRAPPIST-1e sits between those two conditions. Not exposed enough to dismiss, not clear enough to trust. It is the place where the question remains alive because the evidence has become difficult in exactly the right way. And once you feel that, once you understand that the system's most important world is balanced there, between readable failure and unreadable possibility, another factor begins to matter more than ever. If a planet is going to endure under a star like this, it may need not just air. It may need a shield. A magnetic field is one of those planetary features that almost never enters ordinary imagination, which is understandable, because on Earth it is mostly experienced by not being experienced. We do not wake up and feel the magnetosphere holding. We do not watch it as a visible dome above the atmosphere. Most of the time it remains conceptually abstract, a lesson from school, an aurora at high latitudes, a faint mention in discussions about the core. And yet it may be one of the reasons Earth gets to feel ordinary. Without some form of magnetic shielding, a planet orbiting close to an active star is more exposed to the steady abrasion of charged particles and magnetic storms. Atmospheres are not lost in a single theatrical instant. Often they are worn down, heated, dissociated, picked at over time. A protective field does not make a planet invulnerable, but it can change the terms of the contest. It can make erosion slower. It can help a world keep what it is trying to become. So when people ask whether TRAPPIST-1e could still be viable, part of the answer lies in a region no telescope can simply photograph for us. Does the planet generate a magnetic field strong enough, stable enough, long-lived enough to matter? That question leads us down into the interior, because magnetic fields in rocky planets are not surface decorations, they are symptoms of deep internal life. On Earth, the field comes from motion in the liquid outer core, a churning conductive layer driven by heat flow, rotation, and the slow dynamics of a planet that has not yet gone geologically still. A magnetic field, in that sense, is evidence that the inside is still working, still moving, still converting buried energy into planetary consequence. TRAPPIST-1e may have help there from an unexpected source, the very closeness that makes the system dangerous. A close orbit around a star does not just expose a planet to radiation, it also means strong gravitational interaction. If the orbit is even slightly non-circular, the pull on the planet can vary over the course of each revolution, stretching and relaxing the body again and again. That repeated flexing generates internal friction and heat. We know this process in our own solar system from places like Io, Jupiter's volcanic moon, where tidal forces drive such intense internal activity that the surface is continuously remade by fire. TRAPPIST-1e is not Io. It is larger, denser, and far more relevant to the question of habitability. But the principle matters. Tidal heating could help keep its interior active. And an active interior is one of the few things that can do several vital jobs at once. It can power volcanism, which helps replenish atmospheric gases over long timescales. It can keep internal layers mobile enough to maintain a magnetic field. It can prevent the planet from becoming geologically stagnant too soon. This is where the logic becomes beautifully difficult. The same compressed architecture that threatens these planets may also be part of what allows one of them to endure. Too much tidal stress and you get instability, relentless volcanism, climate disruption, maybe even surface conditions too chaotic to settle. Too little and the planet cools, hardens, and loses some of the internal dynamism that might have helped it recover from atmospheric loss. Once again, survival is not one condition, it is balance. TRAPPIST-1e keeps pulling us back to that word. A world like this does not need perfection. It needs enough favourable processes to overlap for long enough shielding, enough outgassing, enough atmospheric retention, enough moderation of day and night, enough liquid water somewhere stable enough to matter, enough time after the worst stellar violence for chemistry to stop being constantly reset. That may sound like a demanding list, and it is. But the reason it feels so powerful here is that we can almost see those requirements assembling and failing in different combinations across the system. The inner planets may represent worlds where too many of those balances were lost. The outer worlds may still hide possibilities we cannot yet interpret well. TRAPPIST-1e is where the balances are close enough to keep the question alive, and that has an emotional consequence. The more we learn about the system, the less we are searching for a mirror of Earth, and the more we are studying thresholds. What is the minimum a rocky world needs to remain climatically connected under a red dwarf? How much punishment can a planet take and still hold on to the ingredients for longer stories? How narrow is the path between an exposed rock and a world with atmosphere, oceans, and chemical continuity? These are not glamorous questions in the old exoplanet headline sense. They are better than glamorous. They are real. If Webb eventually tells us that TRAPPIST-1e is airless, then we will not merely lose a favourite candidate. We will gain a profound boundary condition. One of the most carefully studied rocky planets in a habitable zone around a nearby red dwarf will have failed to retain the very thing many people assumed such planets would commonly possess. That would not mean life around red dwarfs is impossible. It would mean the bar is higher than optimism once liked to admit. If, on the other hand, E does hold a secondary atmosphere, even a modest one, even one unlike Earth's in important ways, then the meaning of that result will also travel far. It would show that the gauntlet can be passed, that a rocky world under an active small star can emerge from the long violence with enough of itself intact to remain climatically interesting. Not an Earth twin, something more useful than that. A survivor. I think that is one of the deepest shifts happening in this field. We are moving from fantasy categories to survival categories. From which planet looks most like Earth to which worlds made it through. That is a more mature question, a sterner one, and it may be the only kind that will ultimately tell us where life can take hold in the galaxy. Because life, at least as we know it, does not begin on an abstractly favourable rock. It begins inside continuity. Stable gradients, repeating cycles, chemistry that is not constantly erased, energy sources that are not purely catastrophic, interfaces where complexity can accumulate rather than merely endure. When we talk about habitability, this is what we mean at depth, even if the headlines rarely say it that way. That is also why subsurface possibilities matter, even though they are harder to dramatize. A planet does not need a blue, open ocean under a bright sky to host interesting chemistry. Hidden water beneath ice, hydrothermal environments below a sealed crust, liquid reservoirs sheltered from stellar punishment, these too belong to the serious landscape of possibility. In our own solar system, icy moons have forced that realization on us. Places once dismissed as too cold, too remote, too sealed off, now look chemically alive in ways earlier generations barely imagined. TRAPPIST-1e could, in principle, hold on to a version of possibility that is not obvious from the surface. So could some of the colder worlds farther out. That does not rescue every hope. It does something more valuable. It broadens the meaning of survivable environments without lowering the standard of evidence. Still, for all those subtleties, there is a reason E remains the emotional centre of this system. It occupies the threshold most people can feel, a rocky, habitable zone world around a nearby star, balanced between atmospheric survival and exposure, between climatic continuity and planetary fracture. Not easy to romanticize anymore. Not easy to abandon either. And because it sits there, everything beyond it begins to change in tone. The outer planets are often described with a softer kind of curiosity, but softness can be misleading. They are not simply calmer because they are farther out. They are colder, dimmer, and more difficult to interrogate. Their signals weaken. Their surfaces, if they have surfaces accessible in any familiar sense, may be governed by different kinds of water, different greenhouse regimes, different internal heat budgets. The farther we go, the less the system feels like a lineup of possible Earths, and the more it becomes a gallery of climate experiments, which is exactly what TRAPPIST-1 has turned into. Not a promise, a test bed. Not a row of homes waiting to be found, but a sequence of worlds asking which combinations of rock, air, water and time can survive around the most common stars in the galaxy. And once you begin to see the system that way, the outer planets stop feeling like bonus material. They become the colder edge of the same question, where atmospheric failure may give way to another kind of uncertainty entirely. Not whether a world lost too much heat, but whether it ever had enough of the right kind in the first place. Beyond TRAPPIST-1e, the system does not become simpler. It becomes quieter, in a way that can fool the imagination. Distance from the star feels, at first, like relief. Less scorching light, less obvious atmospheric stripping, less of that brutal intimacy that defines the inner worlds. And in one sense that is true, but farther out another problem takes over. Cold begins to compete with possibility. The signals weaken. The questions stop being about a world enduring too much and become questions about whether it can remain active enough, warm enough, chemically mobile enough to matter. That is the territory of TRAPPIST-1, F, G and H. These planets receive much less energy from their star than the inner members of the system, and that changes the emotional texture of the search. If B and C feel like exposed evidence, and D feels like the point where disappointment starts to become pattern, then the outer worlds feel almost like sealed rooms. We know they are there. We know they are rocky. We know some of them occupy distances where water in some form remains plausible. But what that water is doing, where it is, how deeply it may be buried, and whether any atmosphere can hold conditions together, those answers are harder to extract. This is where the old headline language about habitable zones becomes especially fragile. People often imagine the habitable zone as a band of comfort, a ring where nature more or less behaves. Yet on the cold edge of such a zone, or beyond it, liquid water can become a much more conditional thing. It may be absent at the surface but stable below. It may appear only in limited regions. It may depend on greenhouse warming, internal heat, pressure effects, or climate states that have no easy analogue in daily human life. A world can have water and still be forbidding. It can even have enormous amounts of water and be less hospitable than a drier, more balanced planet. TRAPPIST-1F brings that lesson into view. It is close enough to remain in the serious conversation, far enough to force different climate questions than the inner planets. Depending on its composition and atmosphere, it could be a place where water is abundant in ways that do not help surface habitability at all. Too much water, especially under the wrong thermal conditions, can mean thick, steam-rich environments, crushing pressures, deep global oceans without the stabilizing influence of exposed continents or layered interiors that separate ocean from rock in ways that disrupt the kind of geochemical cycling Earth depends on. That last point is easy to miss, because water is one of those words that instantly brightens the imagination. But water is not automatically an invitation. Context decides everything. On Earth, water participates in a rich exchange with rock, atmosphere, climate, and the cycling of carbon. It is part of a whole planetary conversation. On another world, water could sit in a form or location that interrupts more than it enables. A planet can drown its own habitability. That is one reason the outer TRAPPIST-1 worlds are so interesting. They force us out of the childish version of the search, where water equals life and habitable zone equals promise. They ask instead whether a world has the right architecture for long-term balance. Too hot, and the atmosphere thins or chemistry breaks down. Too cold, and water retreats or locks away. Too much ocean, and some of the stabilizing exchanges between land, sea, and air may vanish. Too little internal heat, and the world goes still. Every answer opens another threshold. TRAPPIST-1G sits near that outer edge of serious surface habitability discussion, and that makes it one of the system's strangest emotional objects. It has enough distance to escape some of the brutal thermal logic of the inner planets, but not so much distance that the conversation collapses into pure ice world speculation. It remains tantalizing without becoming easy. The world sits there like a distant maybe, not because the evidence strongly points to habitability, but because the evidence has not yet allowed cleaner dismissal. That is a very different kind of hope than people first brought to this system, less exuberant, more disciplined, almost reluctant. And then there is TRAPPIST-1H, the outermost known planet, where the architecture of the system finally opens into something colder and more remote. This is not where most scientists would place their strongest expectations for Earth-like surface conditions. The starlight is weak, the climate possibilities are narrow. Any surface water would need help that is increasingly hard to supply. A hydrogen-rich atmosphere, substantial greenhouse forcing, unusually favourable internal heating, or some other compensating mechanism would have to do an enormous amount of work. Yet even H matters, because it completes the system's emotional shape. The inner planets tell us what stripped worlds may look like. The middle tells us where the knife edge lies. The outermost world shows us the fading margin, where habitability begins to surrender not to heat and erosion, but to cold and insufficiency. The whole system becomes legible as a range of environmental fates around one small star. Not identical planets with different labels, but a compressed atlas of what can happen when rocky worlds are distributed across a narrow-banded distance under a red dwarf sky. And that, in itself, is remarkable. There are not many places where nature has handed us such a concentrated experiment. Same star, similar sizes, tight orbital spacing, multiple rocky worlds arranged across a sweep of conditions narrow enough to compare, yet diverse enough to separate. It is as if the universe built a laboratory out of a solar system and then placed it close enough for us to study with our best instruments. Not close in human terms, of course. 40 light-years is still a staggering separation, but close enough for transit measurements, close enough for thermal phase curves, close enough for this long, slow act of planetary inference. Which is why the TRAPPIST-1 story keeps growing in significance, even when the findings get harsher. It would have been easier, emotionally, if Webb had simply found a clear, thick atmosphere around one of the prime candidates, and given the world a headline everyone could carry intact. But science does not exist to preserve the neatest emotional arc. It exists to sharpen reality. And sharper reality is exactly what TRAPPIST-1 is giving us. The inner worlds are warning us not to romanticize rock, The outer worlds are warning us not to romanticize water. The system as a whole is warning us not to confuse a favorable orbital diagram with a living planetary condition. Once you see that, Earth begins to return to the frame in a different way, not as the center of everything, not as a sentimental contrast, as a control sample. The only inhabited world we know, and therefore the only place where we can study what success looks like after the fact. We are used to Earth. That may be the greatest obstacle to understanding it. Familiarity makes miracles look procedural. A stable atmosphere, active geology, liquid water at the surface, magnetic shielding, long-term climate feedbacks, a star energetic enough to power biospheres, but not so punishing that everything resets. All of that disappears into the background of daily life. We grow up under the result and mistake it for the default. TRAPPIST-1 is part of what breaks that illusion. Every stripped inner world makes Earth feel a little less automatic. Every uncertain atmospheric signal around E makes our own air feel a little more contingent. Every colder outer possibility makes our planet's balance of ocean, land, and climate look a little less inevitable. This is one of the hidden gifts of exoplanet science. It does not only expand the universe outward, it returns us to our own world with stricter eyes. And perhaps that is why the emotional tone of Webb's verdict should not be disappointment, even though many of the easy hopes are fading. Disappointment assumes the point of the system was to make us feel less alone quickly. That was never a fair burden to place on it. TRAPPIST-1 is doing something deeper. It is forcing a more adult question, not how many Earths are out there, but how hard is it for a rocky world to become Earth-like in the ways that matter? Because if life is rare, we need to know why. If it is common, we need to know which worlds actually carry the conditions long enough for biology to begin and endure. Either way, the path runs through systems like this, through atmospheres that survive or fail, through stars that help and harm, through climates that either connect a world into one functioning whole or fracture it into separate physical realities. TRAPPIST-1 is not answering all of that alone, but it is making the stakes visible. And the more visible those stakes become, the more the system feels less like a collection of planets and more like a set of thresholds arranged around a star. That is why, even after we have moved past the hopeful rush of first discovery, the deeper question still tightens around one world in particular. Because the outer planets broaden the field, but they do not quite hold the centre. The centre remains with the planet that stands between the scorched evidence inside and the colder ambiguity beyond. The one place where atmospheric survival, temperate possibility, and scientific seriousness still overlap. Which means the case for TRAPPIST-1e does not weaken when we widen out to the system. It grows heavier. Everything around it makes the middle harder to ignore. And the closer we look at that middle, the more we are forced to ask not just what Webb has already ruled out, but what kind of world could still remain once the easy stories are gone? What could... Not a cinematic fantasy with blue oceans already waiting for us. Not a neat second Earth sitting politely 40 light-years away. The possibilities left for TRAPPIST-1e are more constrained than that, and therefore more interesting. A secondary atmosphere is still on the table. A surface that is partly clement rather than globally mild is still on the table. Water that exists, but not in the broad, easy way people instinctively imagine, is still on the table. A colder world under the influence of methane, or a climate where habitability survives only in regions, or even a subsurface refuge beneath a harsher exterior. All of that remains more defensible than the older dream of a comfortable Earth analogue waiting to be confirmed. A global ocean world under a stable atmosphere would imply one kind of cosmic generosity. A tidally locked planet with a habitable ring of twilight would imply another. A colder world with hidden reservoirs and localized chemistry would imply something else again, something more austere and perhaps more common in the galaxy than our own arrangement. Even an airless result would have meaning, because it would tell us that one of the best nearby tests of red dwarf habitability failed under scrutiny. None of these outcomes are empty. They simply speak different truths. That is the part of exoplanet science people sometimes resist. We want the answer to arrive in the emotional language we already prepared for it. We want life, or at least a world easily narratable as life-ready. We want a horizon we can picture without effort. But reality often moves in another direction. It strips the clichés away before it gives anything back. It insists on precision first, and only after the easy imagination has been disciplined does the deeper wonder appear. TRAPPIST 1e is deep wonder in that stricter sense. Because to appreciate what is still possible there, you have to stop asking whether it resembles the Earth you already know, and start asking what forms of planetary continuity can survive under a star like this. You have to let go of noon and midnight as daily experiences, and imagine them as permanent geographies. You have to imagine climate as something not spread across a rotating globe, but stretched between hemispheres in a long, continuous negotiation. You have to picture water not merely as oceans under clouds, but as an active variable whose location, phase, and mobility decide everything. On a tidally locked world with the right atmosphere, the substellar point, the place directly beneath the star, might be covered in cloud systems that form because strong heating drives upward motion there. Those clouds could reflect some incoming radiation, complicating the planet's energy balance in ways that make the dayside less straightforwardly hellish than simple intuition suggests. Farther from that point, winds might carry moisture and heat outward. On the dark side, cooling would dominate, but not necessarily to the point of total atmospheric collapse if enough transport exists. The result could be a climate system unlike Earth's, yet still coherent, still dynamic, still capable of long-term pattern. That idea matters because it reminds us that habitability is not a single familiar climate type. It is a capacity for stable complexity. The more we study exoplanets, the more we are likely to discover that worlds do not need to look like home to sustain meaningful environmental structure. Some may have permanent storm belts. Some may have oceans under ice. Some may have habitable margins rather than habitable continents. Some may host conditions that are chemically rich but visually alien. If life exists elsewhere, it does not owe us an easy resemblance. Even so, resemblance is hard to stop wanting, because resemblance feels like emotional access. We can imagine standing on a beach. We can imagine rain. We can imagine wind in a sky that curves the way ours does. It is much harder to imagine living on the edge of permanent day, under a red dwarf sun fixed in one place, with the habitability of your world depending on atmospheric transport patterns and a distant band of temperate compromise. Yet that more difficult image may be closer to the truth of many worlds than the beach ever was. And that is one of the reasons TRAPPIST 1e stays in the mind. It forces us toward a more flexible imagination of livable conditions without relaxing the demand for evidence. The evidence at this point is severe but not final. Webb has narrowed the atmospheric options. It has made the easy analogies feel less trustworthy. It has shown us that the star complicates interpretation and that the planet's signal is entangled with a stellar source whose own behavior must be understood in detail. It has placed TRAPPIST 1e into a corridor of possibilities narrow enough to feel real, but wide enough to keep the verdict open. That open verdict is not a weakness in the story, it is the story. Because if science were only valuable at the moment of certainty, most of its greatest emotional power would vanish. There is a special kind of honesty in a frontier where some doors have closed, a few remain open, and everyone can feel the shape of the unknown more clearly than before. We are there now with TRAPPIST 1e. The question is no longer vague optimism, it is structured suspense. Not could anything be true, but which of these shrinking possibilities is the world actually living? That is a much stronger tension than hype. Hype expands possibilities carelessly. Good evidence compresses them until each remaining option matters more. You can feel that compression in the way the system has changed in cultural memory. When TRAPPIST 1 first entered public imagination, it often appeared as a kind of planetary jackpot. 7 Earth-sized worlds, so close together, so nearby in galactic terms. The emotional message was obvious. The universe may be crowded with places almost like ours. That message was not irrational. It emerged naturally from the discovery itself. But discovery is often the beginning of misreading. Initial excitement loves breadth, measurement brings depth, and depth is frequently less flattering. Now the system reads differently. It feels tighter, more conditional, less like a bouquet of chances and more like a sequence of tests. The early planets have become cautionary examples. The outer planets remain difficult, withholding, half concealed behind cold and weak signal. TRAPPIST-1e remains standing in the middle, not because it has been vindicated, but because it has not yet been ruled into sterility with the same force. That is a subtler kind of prominence, but a more meaningful one. It also changes how we should think about the famous phrase, best place to look for life. A best place to look is not always the place most likely to be inhabited. Sometimes it is the place most likely to teach us what is possible. TRAPPIST-1 may prove to be exactly that. Even if none of its planets are ultimately habitable in the fuller biological sense, the system could still end up transforming the search for life by revealing how atmospheres survive, how red dwarf environments sculpt rocky worlds, and how deceptive our first-pass optimism can be. In science, a system can fail as a paradise and succeed as a revelation. There is something almost beautiful in that reversal. We arrive wanting neighbours. We leave with stricter eyesight. And once stricter eyesight enters the story, Earth becomes impossible to leave out for long. Not because this is secretly a story about Earth instead of TRAPPIST-1. It is because every serious exoplanet investigation eventually becomes a mirror held up to the conditions we live inside without noticing. Every time we identify an atmosphere as thin, absent, uncertain, or compositionally strange, our own stops feeling like a given. Every time we imagine a tidally locked climate struggling to remain globally connected, our rotating world of circulating oceans and mobile weather becomes harder to dismiss as ordinary. Every time a nearby rocky planet turns out to be less Earth-like than its size suggested, we are reminded that Earth's most important qualities are not the ones visible in a radius measurement. A planet can be the right size and still miss the whole point. That line may be the quiet verdict hanging over this entire system. And if it is, then Webb has already changed more than a few atmospheric models. It has changed the emotional grammar of the search. Because once you really absorb what TRAPPIST-1 is telling us, the hunt for life stops feeling like a matter of counting rocky worlds in favourable orbits. It starts feeling like a matter of tracing the long, improbable survival of planetary conditions delicate enough to be common in theory and rare in practice. That is a more difficult universe. It may also be the true one. And if it is true, then the path forward becomes both harder and more meaningful. We need more observations, more transits, better stellar models, deeper understanding of atmospheric chemistry under red dwarf light, better constraints on interiors, climate transport, cloud behaviour, and the subtle ways a star can imitate the signal of the world we are trying to read. The search has not become easier because Webb arrived. It has become worthier of Webb. And that worthiness may be the most exciting part of all, because it tells us the search has entered a more serious age. For years, exoplanet science lived in a kind of necessary exuberance. First came the shock that planets were common, then the realization that many of them were unlike anything in our own system. Then the flood of discoveries, hot Jupiters, super-Earths, tightly packed systems, temperate candidates, planets around dim red stars, planets where transit geometry let us infer more than just existence. Each stage widened the map. Each stage made the universe feel busier, less empty, more structurally inventive than older generations had reason to expect. But widening a map and understanding a world are not the same act. Webb marks the point where some of the broad optimism has to report for inspection. That is not a loss. It is what maturity looks like in a science. The field has moved from finding planets to interrogating them, from counting bodies to asking whether those bodies retained air, cycled chemistry, and endured the temperamental history of their stars, from statistical abundance to environmental credibility. Those are harder questions, but they are also the ones that matter if the search is really about life and not just inventory. TRAPPIST-1 sits right at the centre of that transition. The system is close enough and geometrically favourable enough that it can no longer live comfortably inside vague promise. It has become one of the places where the future of exoplanet habitability science is being negotiated in public. Every constraint on an inner planet, every atmospheric scenario narrowed around E, every reminder that the star is both subject and obstacle, all of it contributes to a larger shift in how we think about where life might endure. This is no longer the age of easy candidate lists. It is the age of atmospheric credibility. And atmospheric credibility is a stern standard. A world needs more than a decent location. It needs a history that did not erase itself. It needs feedbacks that do not run away too easily. It needs enough chemical replenishment to survive losses. Enough internal vitality to avoid going inert too soon. Enough moderation that liquid water, if present, can do more than briefly appear and vanish. Most of all, it needs continuity. That word keeps returning because it deserves to. Life does not merely need ingredients. It needs a stable enough stage for those ingredients to remain in conversation for immense stretches of time. TRAPPIST-1 has become a place where we can watch the universe answer whether such continuity is easy or hard around the most common stars in the galaxy. That point is easy to underestimate. Red dwarfs are everywhere. They dominate the stellar population. If habitable worlds commonly persist around them, then the galaxy could be rich in environments where biology has had time, perhaps far more time than Earth has enjoyed, to begin and elaborate itself. But if close-orbiting rocky planets around these stars often end up stripped, climatically fractured, or chemically stunted, then abundance of stars does not translate neatly into abundance of living surfaces. The difference between those futures is enormous, which means that even a negative verdict on TRAPPIST-1e would still echo very far. People sometimes talk about disappointing results as though they shrink the universe. In reality, they usually do the opposite. They make the universe more precisely strange. Suppose Webb and future observations eventually push TRAPPIST-1e toward an airless or nearly airless interpretation. That would not make the system irrelevant. It would sharpen a deep truth. One of the most favourable nearby test cases for red dwarf habitability did not make it. That would force stronger questions about atmospheric loss, planetary magnetic resilience, and whether the habitable zone around such stars is often a misleadingly generous label for worlds whose surfaces cannot remain globally kind. On the other hand, suppose E turns out to possess a genuine secondary atmosphere, perhaps not Earth-like, perhaps not globally mild, perhaps compatible only with limited surface liquid water or unusual climate circulation. That result would be equally profound. It would tell us that the path, though narrow, exists. A rocky world under a star like this can come through the long violence with enough coherence left to keep the possibility alive. The system would become not a warning alone, but a map of the dividing line between survival and failure. That is why the verdict matters so much. Not because it crowns a new Earth, but because it teaches us where reality draws its thresholds. Thresholds are easy to ignore in daily life because Earth hides so many of them inside normal experience. We do not think of our atmosphere as a survival threshold when we step outside and breathe. We do not think of ocean circulation as a threshold when the seasons arrive more or less on time. We do not think of our magnetic field as a threshold when solar particles glance harmlessly away overhead. We inherit the result of many successful balances and call it the world. Only when we study other planets do we start seeing how many separate things had to work well enough, long enough, at once. A single bad comparison can clarify that. Mars is rocky, Venus is rocky, Earth is rocky. Those three facts are superficially equal, and yet anyone who has absorbed even a little planetary science knows that the lived reality of those worlds is violently different. Mars likely lost much of what once made it wetter and more open. Venus crossed into a surface hell so complete that its size and composition become almost irrelevant to human intuition. Earth sits between them, not by entitlement, but by outcome. That lesson has always been in our own solar system. TRAPPIST-1 extends it, compresses it, and forces it into a more systematic form. Here, multiple Earth-sized rocky planets crowd one small star, and the differences among them are emerging not as aesthetic curiosities, but as atmospheric verdicts. It is as if the universe has taken the old Mars-Venus-Earth lesson and rewritten it at higher pressure. Same system, same star, same basic class of planet, Very different fates. Once you grasp that, the search for life gains a new kind of gravity. It stops being a treasure hunt for lookalikes and becomes an inquiry into planetary biography. What did this world lose? What did it keep? What rebuilt after the first losses? What internal processes stayed active? How did the star age, and how badly did that aging matter? Did climate ever achieve a long equilibrium, or was it repeatedly broken before complexity could take hold? These are not the questions of romance. They are better. They are the questions that take the universe seriously. And taking the universe seriously does not diminish awe. It changes its source. Early awe comes from abundance in scale. Later awe comes from contingency. From realizing that the conditions under which a planet becomes more than stone may be narrower, more fragile, and more historically burdened than we wanted to believe. That kind of awe is quieter. It lingers longer. It is the feeling TRAPPIST-1 increasingly produces. Not wonder that erupts and burns off, but wonder that tightens. You start with the headline and end with a more difficult respect. Respect for how subtle atmosphere detection really is. Respect for how entangled planets are with the lives of their stars. Respect for the possibility that even nearby rocky worlds in good orbital neighborhoods may be far harsher than their initial discovery summaries implied. Respect, too, for the astonishing fact that our species is already capable of learning any of this at all. That fact deserves more attention than it usually gets. 40 light-years is far enough that the light arriving from TRAPPIST-1 tonight left before most people watching were born. Those photons crossed an emptiness almost impossible to feel at human scale, and when they arrive, we do not merely greet them, we dissect them. We use them to ask whether a planet the size of our world, crossing a star smaller than our Sun, carries gases in a thin shell around its surface. We ask whether those gases are thick or thin, light or heavy, redistributing heat or failing to do so. We ask whether the world beneath them could be globally connected or climatically broken. This is an extraordinary thing for matter to have taught itself to do. It does not make us masters of the cosmos. It makes us witnesses, becoming more competent. That, perhaps, is the most emotionally accurate place to stand as Webb's verdict on TRAPPIST-1 comes into focus. Not triumphant, not defeated. More competent than before, less naive, better able to distinguish projection from evidence, and therefore better able to see real possibility when it survives the filtering. The easy hopes are not the ones worth keeping anyway. The valuable hopes are the ones that remain after the data has done its work. TRAPPIST-1e still carries that kind of hope. Not the hope of immediate vindication, but the hope of a world whose true nature has not yet collapsed into certainty, whose remaining atmospheric possibilities are narrow enough to matter, and whose fate will help define how we think about habitability around the galaxy's most common stars. That is enough to hold attention. More than enough, because the next measurements will not merely add details, they will continue a sorting process already underway, separating worlds that only looked promising from worlds that may have held on. And once you understand that, you realize the story was never really about whether TRAPPIST-1 would hand us an easy answer. It was about whether our instruments could finally teach us how unforgiving the real question had always been. And that question is unforgiving, because life is not competing with emptiness. It is competing with physics. That may be the clearest lesson hidden inside Webb's verdict. When people imagine the search for life, they often imagine a simple branching path. Either a world has the right ingredients, or it does not. Either it sits in a favourable zone, or it does not. Either it resembles Earth enough to keep hope alive, or it falls away from consideration. But the universe is not arranging planets into neat bins for our convenience. It is running countless long experiments in heat flow, atmospheric escape, chemistry, gravity, radiation, cloud formation, tidal forcing, magnetic shielding, and deep interior evolution. Life, if it appears, has to emerge from within those experiments without being erased by them. That is why a rocky planet can seem promising from a distance and still fail under scrutiny. Promise is often geometric. Life is historical. TRAPPIST-1 has become one of the places where that distinction stops being philosophical and turns measurable. We can feel it in the harshness of the inner worlds, in the uncertain edge where E remains suspended, and in the colder ambiguity beyond. The system no longer looks like a generous row of possible homes. It looks like a compressed map of what rocky planets go through when they are born around a small star whose light is useful, whose size is observationally convenient, and whose temperament may be deeply costly. In that sense, Webb's verdict is not just about TRAPPIST-1. It is about the broader exoplanet era growing up. The early phase of discovery had a certain innocence to it. Find enough worlds, and eventually, one of them will resemble Earth closely enough to reassure us. Count enough candidates, and abundance itself becomes comforting. The modern phase is different. We are learning that the challenge is not merely to find rocky planets in the right locations. The challenge is to understand which ones remained intact long enough for complexity to settle. That requires a more severe imagination, one willing to see that planetary success may depend on sequences of good fortune we do not personally feel because we were born inside one. Earth, in other words, has hidden its own difficulty from us. We tend to think of our planet as the baseline, the thing against which other worlds are measured. But Webb's work on systems like TRAPPIST-1 encourages a more unsettling view. Earth may not be the baseline at all. It may be an outcome, a particular planetary biography in which atmosphere, water, rotation, interior heat, magnetic shielding, and solar behavior remained compatible enough for long enough that life could stop merely resisting the environment and start elaborating itself within it. If that is true, then the search for life is not just a search for the right kind of planet. It is a search for the right kind of planetary history. TRAPPIST-1 helps expose that because its planets are similar enough in the ways headlines notice and different enough in the ways reality cares about. They are rocky, they are roughly Earth-sized, they orbit the same star, and yet the likely outcomes diverge sharply. That divergence is the whole point. It tells us that size is not destiny, and location is only the opening bid. The rest is atmospheric survival, thermal continuity, stellar weather, interior resilience, chemical renewal, and time. So much depends on time. Not time in the broad sentimental sense, but time as pressure. Time for the star to calm. Time for the atmosphere to form or reform. Time for water to stabilize into a meaningful role. Time for climate to stop resetting. Time for chemistry to accumulate structures that can persist. A planet may spend billions of years failing before it spends millions succeeding. Or it may spend billions failing and never cross the threshold at all. Around a red dwarf, the durations can become even stranger. The star may outlive the current age of the universe many times over, while the worlds nearest it spend their early eras being stripped, heated, and tested. This is where the system begins to acquire a nearly tragic dignity. Not because it is doomed, but because it reveals how much a world may have to survive before it earns the calm conditions we so casually associate with habitability. We are used to thinking of stars as providers of light and warmth. TRAPPIST-1 reminds us that they are also sculptors, disciplinarians, and sometimes destroyers. A planet's star is not just the lamp above the landscape. It is part of the landscape's making and unmaking. That is especially important for anyone tempted to hear red dwarf and long-lived as automatically hopeful together. A long future does not erase a violent youth. It may only make the contrast sharper. The worlds that endure around such stars may be extraordinarily persistent, but the worlds that do not may still be numerous, still rocky, still close to what headlines would once have called promising. The gap between those descriptions and lived planetary reality is exactly the gap Webb has begun to illuminate. That illumination is a strange kind of gift. It does not flatter our hopes. It educates them. You can feel that education in the language itself. Years ago, the system encouraged phrases like best chance, Earth-like, potentially habitable, and search for alien life in their broadest, easiest form. Those phrases are not useless, but they are now less sufficient. Today the conversation sounds more exacting. Airless daysides, weak or absent thick atmospheres, secondary atmospheres, stellar contamination, thermal phase curves, heat redistribution, methane scenarios, tidal locking, magnetic shielding. These are not colder words, they are warmer, in the sense that they bring us closer to the real fire of the problem. They also make the system more unforgettable, because what is memorable is not that TRAPPIST-1 once seemed promising. What is memorable is the way promise is being refined into a series of planetary judgments. The innermost worlds are not just bad candidates, they are demonstrations of atmospheric vulnerability. The colder worlds are not just mysterious, they are reminders that water and distance create new complexities rather than simple relief. And E, standing in the middle of all this, is no longer just the likely favourite. It is the world whose fate may tell us whether a rocky planet around a small active star can hold a globally meaningful climate at all. That is a much bigger title payoff than simple confirmation would have been, because the phrase JWST's verdict sounds, at first, like a headline seeking closure. But the true verdict is more sophisticated than closure. Webb has already ruled against the easy version of the TRAPPIST-1 dream. It has ruled against assuming that Earth-sized means Earth-ready. It has ruled against the idea that habitable zone membership tells a sufficient story. It has ruled against the comfort of talking about planets without taking their stars personally. And in doing so, it has opened the real case. Under what conditions does a rocky world around a red dwarf remain atmospherically alive? That case is still open, but it is now open in the right way. One of the beauties of good science is that it makes ignorance more precise. Bad ignorance is fog, good ignorance has edges. We now know more clearly what TRAPPIST-1b is not, more clearly what C likely lacks, more clearly that D is not carrying the kind of atmosphere people once wanted for it, more clearly that E remains important, because its remaining possibilities are both limited and consequential. More clearly that the star itself is a serious interpretive actor. More clearly that the system's meaning extends beyond whether any one planet hosts life. That kind of precision changes how a mystery feels. It becomes less like a fantasy playground and more like a mountain face, where the remaining routes are difficult but real. And that may be why the story stays emotionally powerful, even without an easy triumph. We do not actually need the universe to flatter us in order to be moved by it. Often the opposite is true. A harsher universe, honestly seen, can produce a deeper feeling than a convenient one. It can make the search feel earned. It can turn wonder away from wishful thinking and toward disciplined encounter. TRAPPIST-1 is becoming that kind of encounter. The system is teaching us that what we are looking for is not simply another Earth. We are looking for planetary endurance of a very particular kind. A world that kept enough of its atmosphere, enough of its water, enough of its internal motion, enough of its climatic coherence, long enough for chemistry to do something more than survive. A world that became continuous instead of broken. A world that remained one world rather than splitting into hostile geographies. A world that passed through the violence without losing the possibility of becoming complicated. That is a demanding vision of habitability. It should be. Because if life exists elsewhere, especially around common stars like red dwarfs, then it has already done something extraordinary before it ever produces a single cell. It has inherited a world that made it through. And the closer Webb looks at TRAPPIST-1, the more that phrase begins to matter. Made it through? The question now is whether he did, or whether the entire system, in its own different way, is about showing us how hard that can be. If the entire system is showing us how hard that can be, then it may end up doing something more valuable than confirming a habitable world. It may teach us how to recognize one without fooling ourselves first. That is not a small achievement. In any science, the hardest thing is often not discovering new objects. It is learning which intuitions have to die before the objects can be understood clearly. TRAPPIST-1 has been quietly performing that service for years. It arrived wrapped in one of the most alluring packages astronomy could offer. Nearby, compact, 7 rocky planets, several in the habitable zone, all orbiting the most common kind of star in the galaxy. The discovery seemed to hint not just at possibility, but at abundance. Not just at a target, but at a pattern that might repeat everywhere. What Webb has done is force that pattern to earn itself. And as it turns out, Earning it is difficult. The harsh inner worlds are part of that difficulty. They tell us that being rocky is not enough, being close is not enough, and being easy to observe may come at the cost of living too near a star that shaped them too violently. The uncertain middle is part of that difficulty. It tells us that even the best candidate can survive only as a narrowed question, a small set of atmospheric scenarios under active pressure from evidence. The colder outer worlds are part of it too. They remind us that distance is not salvation. Move farther out and you do not leave complexity behind. You inherit new forms of it. By now the system has almost become a moral lesson in scientific restraint, though not in the cheap sense of don't get excited. Excitement is not the problem. The problem is laziness of imagination. It is the temptation to hear Earth-sized and stop there, to hear habitable zone and stop there, to hear red dwarf and long-lived, and let abundance perform too much of the reasoning. Webb has not asked us to be less amazed, it has asked us to be amazed more accurately. There is a difference. Accurate amazement is quieter at first. It does not rush to claim neighbours. It does not project continents into darkness or clouds into every unresolved spectrum. It waits. It studies the relationship between the planet and its star. It pays attention to atmospheric escape, to climate circulation, to what a thermal phase curve is really saying about how heat moves or fails to move. It recognizes that if a world is tidally locked, then a climate is not just a temperature average. It is a problem of connection. Can the globe function as one system, or has physics split it into permanent extremes? That question alone is worth dwelling on, because it contains a hidden emotional truth. A world is not merely a sphere of rock. It is a sphere whose distant regions must somehow remain in conversation. Day must be able to affect night. Surface must be able to speak to sky. Interior must be able to replenish what the exterior loses. Water must be able to move, to change phase, to carry consequence rather than simply collect. Atmosphere must mediate, translate, soften, and transport. When those conversations fail, what remains may still be a planet, but it is no longer a whole one in the sense that matters for habitability. That is why the phrase globally meaningful climate feels so important around TRAPPIST-1. We are not merely wondering whether some patch of the surface might, in principle, be temperate under one atmospheric model. We are asking whether the planet can act like one connected environmental body, whether enough heat reaches the dark side, whether enough pressure holds, whether enough water remains mobile, whether enough atmospheric chemistry persists, whether enough of the planet talks to itself. A biosphere, at least any biosphere we would recognize as substantial, likely prefers connected worlds to fractured ones. This is one reason Earth keeps returning to the frame without needing sentimental help. Earth is connected in ways so ordinary to us that we barely notice them. Warm air moves, cold air sinks. Oceans carry heat across enormous distances. Water evaporates, condenses, falls, freezes, melts, and repeats. Carbon moves between rock, ocean, sky, and life. Seasons shift not because one hemisphere is permanently condemned to darkness, but because the whole globe rotates under a day that keeps returning. The climate can fail in local and historical ways, but the planet itself is one operating conversation. Seen from the perspective of TRAPPIST-1, that is not ordinary. It is extraordinary. And it becomes more extraordinary the more carefully we look elsewhere. That may be the most emotionally potent reversal in the whole story. Many people came to exoplanet science hoping it would make Earth feel less special. In one sense it has. Earth is no longer the only conceivable rocky world, no longer the only place where oceans and atmospheres might, in principle, have existed. But in another sense, the field has done the opposite. It has made the specific quality of Earth's success feel more improbable, not less. Not unique in any final cosmic sense, perhaps, but certainly not cheap. TRAPPIST-1 contributes to that realization by being so close to promising and so resistant to simplification. If the system had been obviously barren from the beginning, it would not have cut as deeply. If it had immediately yielded a clear Earth-like atmosphere somewhere in the middle, it would have been wonderful, but in a simpler register. Instead, it sits in the harder place, close enough to tempt us, difficult enough to educate us, rich enough in planets to feel statistically meaningful, severe enough in its verdicts to force a revision of instinct. It is almost the ideal system for teaching the field how not to lie to itself. That matters for what comes next, because TRAPPIST-1 is not the end of this story. It is one of the first truly high-profile cases in a long-coming era where exoplanets stop being points on a census and start becoming atmospheric histories. Webb will continue to observe. Analysts will continue to refine stellar models, disentangle contamination, improve retrieval methods, and test climate scenarios. Other telescopes will contribute. Future observatories, built with habitability and biosignatures more explicitly in mind, will inherit a world of exoplanet science made tougher and smarter by systems like this one. And when they do, the lesson they inherit will be clear. Do not ask only what a planet is. Ask what it survived. That may become the defining habitability question of the century. What did it survive during the star's youth? What did it lose? What was rebuilt? Did the interior stay active? Did magnetic shielding endure? Did climate settle into long continuity or remain trapped in unstable extremes? Did water remain in the right conversations with rock and sky? Or did it hide, boil, freeze, or become too isolated to matter? Those are the filters through which future worlds will likely be understood, and TRAPPIST-1 is already helping sharpen them. There is something deeply satisfying in that, even if it is not the satisfaction of immediate answers. A science becomes mature when it learns which questions are worthy of its tools. Webb could have been spent on easier emotional victories, softer stories, vaguer hope. Instead, part of its legacy is becoming this: the careful destruction of lazy analogies, the insistence that a nearby rocky world must prove itself in atmospheric terms, the revelation that thin layers of gas, planetary interiors, and stellar moods matter at least as much as orbital distance. The conversion of wonder into discipline. That is why I think the verdict on TRAPPIST-1, taken honestly, is already in even before the final atmospheric arguments are settled. The verdict is not that life has been found. It is not that the dream has failed. It is that the old, simple version of the dream is over. What replaces it is better. A harder picture, yes, a narrower one, but also a more meaningful one. In that picture, TRAPPIST-1 is no longer a row of vaguely possible Earths. It is a line of planetary outcomes under pressure. Inner worlds teaching us what stripping looks like. Outer worlds asking what cold hides. A middle world holding the question open in the only way worth trusting. Not through hype, but through resistance to dismissal. And above all of them, a small star whose intimacy gives us data and danger in the same gesture. That is a real cosmic story. Not the easiest one, a better one. Because the universe does not become more profound when it gives us quick reassurance. It becomes more profound when it reveals that habitable worlds may be the product of long, improbable endurance, and that we now have the tools to begin tracing that endurance across interstellar darkness. TRAPPIST-1 is part of that tracing. Not a final answer, a turning point. And once you feel it that way, the night sky changes a little. Not because one faint red star suddenly contains proven life, but because it contains a clearer version of the question. 40 light-years away, a small system of rocky planets is forcing us to confront how many gates a world must pass through before it becomes more than stone. How many things can go wrong? How much has to hold? How different promise looks once the evidence begins to speak. That is what Webb has really delivered here. A stricter imagination. A stricter imagination changes more than the way we talk about exoplanets. It changes the emotional scale of the entire search. Before instruments like Webb, distance itself did much of the work. Anything beyond our solar system lived in a zone of abstraction. Planets were possibilities before they were places, and possibility is generous by nature. It lets the mind paint over uncertainty with whatever it most wants to see. But the moment a telescope begins separating atmospheric scenarios, measuring dayside temperatures, constraining heat transport, and exposing the influence of a star's own activity on the signal, the generosity starts to thin. Not because wonder disappears, but because it is no longer allowed to float free of consequence. That is what has happened to TRAPPIST-1. The system has gone from sounding like a rumour of abundance to feeling like a test of planetary seriousness. And that phrase matters. Planetary seriousness. Some worlds invite fantasy because we know too little. Others demand seriousness because we know just enough to understand the stakes. TRAPPIST-1 now belongs to the second category. Every new piece of evidence weighs on the larger question of what a rocky world must retain, rebuild, and protect if it is ever going to become hospitable in the deeper sense. The search is no longer satisfied by silhouette alone. A radius and an orbit are not enough. The older age of exoplanet discovery sometimes made it sound as though life was mostly a matter of finding enough rocky planets and waiting for the statistics to become emotionally comforting. There was truth in that excitement. Numbers matter. The galaxy does appear full of planets, and rocky ones are not rare curiosities. But the deeper science was always waiting in ambush. A rocky planet can be common, and a habitable world can still be hard. Once you admit that, the search gains a different gravity. TRAPPIST-1 is where that gravity becomes visible, because this is not a case where distance alone preserves mystery. The mystery survives contact with detail. In some ways, it becomes stronger there. We know the inner planets have likely lost the easy claim to substantial thick atmospheres. We know the star's behaviour complicates interpretation. We know E remains compelling precisely because the obvious stories about it have narrowed. We know the outer worlds are cold enough and faint enough to resist simple reading. And what emerges from all of that is not a smaller story. It is a more exact one. A planet has to hold together. That may be the sentence most worth carrying out of this system. A planet has to hold together not just physically, but environmentally. Its atmosphere cannot be an afterthought. Its star cannot be treated as background scenery. Its interior cannot be imagined as irrelevant once the surface has formed. A world is a negotiation among layers, timescales, and assaults. The sky above it, the rock below it, the water within and across it, the radiation striking it, the magnetic structure surrounding it, the orbit that governs its geometry of light and dark. All of these are in conversation. Break too many of those conversations, and the result may still be scientifically rich, but it becomes poor territory for life. There is something almost sobering in realizing how narrow that margin can be. Not discouraging, sobering. The distinction matters. Discouragement implies that the search has been damaged by difficulty. Sobriety means the search has been clarified by it. When we learn that some of the most famous rocky worlds in the sky may be bare, or climatically fragmented, or only ambiguously protected by atmosphere, we are not watching hope fail. We are watching hope become more expensive. And expensive hope is usually the only kind worth trusting. This is also why TRAPPIST-1 resists cheap emotional packaging now. It is too mature a subject for the old style of excitement, too full of real physical stakes. If one of these planets eventually turns out to host a stable secondary atmosphere, then the result will mean more, precisely because so much easy optimism has already been burned away. If none of them do, the system will still stand as one of the most illuminating planetary case studies we have ever had. A place where 7 rocky worlds under one star taught us how severe the passage from planet to habitable world may actually be. There is a kind of intellectual integrity in that outcome that I find deeply moving. The universe is not obliged to comfort the stories we tell about it. It is not obliged to place life on our most photogenic candidates or preserve our favourite analogies. What it can do, if we are patient and capable enough, is let us see the structure of reality more clearly than we did before. TRAPPIST-1 has already done that, and the clarity extends beyond astronomy. Once you start thinking in these terms, it becomes harder to take anything stable for granted. Not just on planetary scales, but in a more intimate way. We live inside systems of continuity all the time. Air circulates. Temperatures stay within narrow bounds. Oceans move unseen heat. Geological and biological cycles interlock. The body itself survives on balance after balance, each one so familiar that it becomes invisible until it fails. That may be why exoplanet science feels so unexpectedly emotional when it is done well. It teaches us that the ordinary is often the name we give to successful complexity we have stopped noticing. TRAPPIST-1 makes Earth feel less like a generic example and more like a sustained achievement. Not an achievement in the moral sense, an achievement in the physical sense. A world that for billions of years has remained connected enough to host layered forms of change without losing its underlying continuity. That continuity is not perfect, and never was. Earth has seen catastrophes, extinctions, climate upheavals, ice ages, impacts, and enormous chemical transformations. But through all of it, the planet remained a world rather than dissolving into incompatible conditions. The atmosphere persisted, water remained mobile, the interior kept participating. The star above, for all its power, did not erase the possibility of long biological time. Set beside TRAPPIST-1, that begins to look less routine. And that is part of why this system will stay important, no matter what the final verdicts become on individual planets. It is already changing our sense of planetary normality. It is already teaching us that the search for life cannot be reduced to catalogues and zones. It must become a science of survivable continuity. That phrase too may be worth holding on to. Survivable continuity. Not just the presence of ingredients, not just the absence of immediate catastrophe. A long, durable state in which a world remains sufficiently connected to let complexity deepen rather than merely persist from one crisis to the next. If life is widespread, worlds with survivable continuity may be its true homes. If life is rare, then failures of that continuity may explain a great deal. Either way, TRAPPIST-1 matters. It matters because it is one of the few places where we can watch those ideas harden from theory into evidence. It matters because the system is close enough for repeated scrutiny, compact enough for comparative logic, and difficult enough to resist the seduction of early simplifications. It matters because the small red star at its center is not an incidental host, but an active participant in the fate of every world around it. And it matters because the one planet still carrying the most disciplined hope, TRAPPIST-1e, does so in a way that forces us to confront exactly how little we should romanticize the word habitable. The next rounds of data will matter for all the obvious reasons. Better constraints on the star, better interpretation of transit spectra, better atmospheric retrievals, better climate models, perhaps stronger limits on methane, carbon dioxide, or the thermal structure of the planet. Perhaps a more decisive movement toward one scenario or another. But beneath those technical advances lies something simpler and larger. Every new measurement is part of a long attempt to answer whether one rocky world around one red dwarf held together well enough. That is an astonishing sentence. It is astonishing not because it sounds dramatic, but because it is already real. We are already there. We have already built the instruments, made the observations, and entered the phase where planetary survivability across interstellar distance can be argued in detail. The question is no longer science fiction. It is spectroscopy, thermal emission, stellar contamination models, orbital geometry, atmospheric transport, and patience. That combination may not be as immediately cinematic as "we found another Earth." It is more beautiful than that. It is the beauty of a civilization learning to ask reality its hardest questions in the right language. And if TRAPPIST-1 has taught us anything so far, it is that reality answers best when the language is strict. Strict language does not make the universe feel colder. It makes it feel earned. That may be the finest thing Webb has done for TRAPPIST-1. It has taken a system that could have remained a collage of hopeful adjectives and turned it into a place with consequences. Rocky, tidally locked, atmosphere or no atmosphere, heat redistributed or stranded, water mobile or trapped, star helpful, star harmful. Every term now carries weight. Every possibility implies a climate, a surface, a planetary history. The romance has not been removed. It has been put under load, and whatever survives that load becomes much more powerful. There is a quiet dignity in that process. We begin with desire, as we often do. Desire for another Earth. Desire for neighbours. desire for the ancient question of life beyond our world to become less abstract and more local, less a matter of philosophy and more a matter of coordinates. Then the measurements arrive, and desire has to learn discipline. Not all rocky worlds keep air. Not all habitable zones produce habitable surfaces. Not all long-lived stars are generous in the eras that matter most. The dream does not disappear. It becomes harder to counterfeit. That is the emotional shape of TRAPPIST-1 now, a place where counterfeit hope is slowly being removed from circulation. And once that happens, a deeper form of wonder becomes available. You start noticing how extraordinary it is that so much of the drama lives inside things human senses cannot directly perceive. Not mountain ranges, not seas, not visible weather spiraling across a disk in a telescope eyepiece. The real suspense is in gases, heat transport, ultraviolet histories, tidal stresses, magnetic persistence, and the spectral behaviour of a star that keeps interfering with the evidence we want from its planets. What kind of civilization reaches the point where such things become part of its emotional life? Ours does. That is a remarkable development in the history of matter. We are, after all, creatures who evolved under one atmosphere, one gravity, one day-night cycle, one sky. Our intuitions were trained locally. Every serious exoplanet study is an argument with those intuitions. TRAPPIST-1 may be one of the best arguments we have found. It takes nearly every instinctive shortcut people bring to planetary habitability and puts pressure on it. Earth-sized does not mean temperate. Temperate does not mean globally stable. Water does not mean accessible. Distance from the star does not mean safety. Long stellar life does not mean a planet had an easy beginning. Even a promising candidate can refuse to resolve into anything simple. And yet the system does not collapse into nihilism. That is important. A harsh lesson is not the same as a hopeless one. TRAPPIST-1e remains the proof of that. Not proof of life, not proof of a breathable sky or a broad ocean reflecting red light. Proof that the scientific question still lives in a meaningful place. That one world, at least, has not been swept cleanly into the same category as the harsher inner planets. Its possible futures remain constrained but plural. That means the line between failure and survivable continuity has not vanished from view. It is still there, faint but real, and the field is learning how to see it. There is something beautiful in the fact that one of the most important worlds in modern astronomy is important not because it has already delivered its secret, but because it has resisted premature interpretation. That kind of resistance is healthy. It makes the science better. It makes the eventual answer, whatever it is, more durable. A world that survives skepticism is far more interesting than a world that only survives headlines. And skepticism here is not cynicism. It is respect for the difficulty of the universe. The universe is under no obligation to arrange itself into stories with convenient timings and clear villains. The star that enables observation is also the star that may have stripped the planets bare. The close-in geometry that makes transits easy is also the geometry that likely leads to tidal locking and environmental extremes. The long lifetime that sounds promising may conceal a catastrophic youth. A candidate can be both promising and endangered in the same breath. That is not narrative confusion. It is reality refusing simplification, which is why the system lingers in the mind as more than a set of facts. It becomes a pattern of pressures. You can almost feel them layered on top of one another. Stellar radiation pressing down from above, internal heat pushing up from below, atmospheric escape pulling outward, gravity trying to hold things close, day and night locked into permanent opposition, chemistry either accumulating or being erased. Over and over, the worlds of TRAPPIST-1 seem to ask the same question in different accents. Under these conditions, what can stay whole? That question may be one of the deepest in all planetary science, because wholeness is easy to underestimate. We are trained to think in parts: atmosphere, ocean, core, orbit, star. But a habitable world is not just the presence of those parts, it is their sustained cooperation. A climate is not a collection of ingredients, It is a working relationship. If the sky can no longer carry enough heat to the dark side, if water becomes too isolated, if the star strips too aggressively, if the interior falls quiet too early, if magnetic protection weakens, then the planet may not fail all at once. It may simply stop being the kind of place where complexity can deepen. Life, if it ever had a chance, may lose it not in a single catastrophe, but through the gradual breakdown of planetary conversation. That is one reason the search for life is so much harder than the search for planets. Planets can be counted. Conversations have to be inferred. Webb is giving us better ears for those conversations. Not perfect ears, not final ones, but better. Sensitive enough to tell when the old assumptions are no longer adequate. Sensitive enough to reveal that the inner worlds likely do not speak climatically in the ways we hoped. Sensitive enough to keep TRAPPIST 1E in the frame, without granting it easy innocence. Sensitive enough to show that the search, from this point onward, will belong to patience and precision as much as to grand speculation. That may sound austere, but it carries a kind of tenderness too, because patience is what you practice when something matters enough not to rush. Precision is what you practice when reality matters more than performance. In that sense, the best exoplanet science already contains its own ethics. Look carefully. Separate what is wanted from what is warranted. Let the star be difficult if the star is difficult. Let a planet remain unresolved if it is unresolved. Do not turn a possibility into a verdict before the evidence has passed through enough hands, enough models, enough doubt. TRAPPIST 1 deserves that kind of care. It has earned it. And maybe that is another hidden reason the system feels so compelling. Not because it is easy to imagine living there, but because it is easy to imagine learning from it for a very long time. This is not the kind of subject that becomes smaller when initial hopes get complicated. It becomes deeper. Each layer of realism exposes another layer beneath it. Atmospheric survival leads to stellar history. Stellar history leads to planetary interior dynamics. Interior dynamics lead to magnetic questions. Magnetic questions lead back to atmospheric endurance. Tidal locking leads to climate geometry. Climate geometry leads to water placement. Water placement leads to chemistry. Chemistry leads, eventually, to life or its absence. Everything touches everything else. That is the opposite of disappointment. It is a kind of intellectual abundance more durable than the emotional abundance of early headlines. A narrower corridor of real possibilities can contain more meaning than a wide field of fantasies, because reality has structure. It can be learned. It can push back. It can surprise us in ways that remain true after the excitement fades. TRAPPIST 1 has started doing exactly that. It has pushed back on the casual optimism that accompanied its discovery, but not in a spirit of denial, in a spirit of clarification. It has shown us that some of the galaxy's most inviting-seeming worlds may still be physically severe. It has shown us that Earth-like size can hide utterly un-Earth-like outcomes. It has shown us that the search for life around red dwarfs may depend on the survival of delicate atmospheric conditions through a long hostile beginning. And it has shown us that one nearby planet, just one, can carry extraordinary importance simply by refusing to fit neatly into the easier stories. That refusal is where the final emotional weight of this system may reside. Not in an answer already delivered, but in the discipline of waiting for the right one. Waiting in a story like this is not empty time. It is part of the revelation. We are used to thinking of discovery as a moment, a date, a headline, an image, a sharp sentence that collapses uncertainty into something shareable. But some of the most important discoveries do not arrive that way. They arrive as a long tightening, a gradual refusal of bad explanations, a series of constraints that make the remaining possibilities more charged with meaning than any early fantasy ever was. TRAPPIST 1 belongs to that second kind of discovery. Its drama has never really been in the announcement. It has been in the narrowing. And narrowing, when it is done well, can feel almost spiritual without needing to become sentimental. Not because it reveals destiny, but because it reveals structure. It shows that reality is not an endless field of anything-goes speculation. It has shape. It has limits. It permits some worlds and not others. It lets some atmospheres survive and strips others away. It allows some climates to become connected and leaves others fractured. The more closely we look, the more those permissions and refusals begin to emerge. That is what Webb has really brought to TRAPPIST-1. Not certainty, but shape. The system has shape now in a way it did not before. The innermost planets are no longer generic maybe worlds. They have become evidence of harsh outcomes. The star is no longer just a convenient dim red host. It is a force that both reveals and confuses, both illuminates and endangers. The outer planets are no longer vaguely promising extras on the edge of a good headline. They are colder, fainter territories where different thresholds take over. And in the middle, TRAPPIST-1e remains poised in that scientifically precious state between dismissal and confirmation, where every remaining atmospheric possibility carries real weight. That is an extraordinary place for a world to occupy in the human mind, not because it flatters us, but because it asks something better of us than flattery. It asks for patience strong enough to remain curious after the easy dream has thinned out. And perhaps that is the deepest difference between fantasy and science. Fantasy wants a world to mean what we hoped it would mean. Science waits to find out what kind of world it actually is, even if the answer comes slowly, even if the first reward is not comfort, but correction. TRAPPIST-1 has already corrected us in important ways. It has corrected our tendency to confuse size with familiarity. It has corrected our use of habitable zone as though it were a verdict. It has corrected the soft assumption that long-lived stars are straightforward gifts to the search for life. It has corrected the idea that a rocky planet near us must be emotionally legible before it is physically understood. And after all those corrections, the system has not become less beautiful. It has become more difficult, and therefore more beautiful. Because difficulty, in this context, is not an obstacle to wonder. It is the source of its maturity. A mature wonder is one that can survive bad news, one that does not collapse when a favoured planet looks airless, when a thermal curve suggests poor heat transport, when a star contaminates the signal, when the best candidate remains unresolved. A mature wonder understands that these are not failures of the universe to entertain us. They are the universe becoming more itself in our understanding. There is dignity in that. There is also intimacy. Strange as it sounds, the stricter the evidence becomes, the closer the system feels. Not visually closer, intellectually closer. We are no longer just gazing at a famous name in the sky. We are engaging with a specific set of planetary realities. 40 light-years is still an immense distance. No human body will casually bridge it. No naked eye can read an atmosphere there. The star itself is too faint for ordinary attention. And yet the system has entered our inner life with startling force. We talk about day sides and night sides there, about possible winds there, about the survival or loss of air there, about hidden oceans, dark hemispheres, red light fixed in the sky, and the question of whether one small rocky world held on to enough continuity to remain more than exposed stone. That is a profound extension of human presence, not physical presence, but interpretive presence. We have reached that far with attention. Attention may be one of the great themes of this whole story. Webb is an instrument of attention. It does not make reality kinder, it makes it sharper. It attends to faint changes in light with almost absurd precision. It lingers where a noisier age of astronomy could only gesture. It asks the sky for less obvious truths, and in return, the sky offers something subtle and severe. Not another easy Earth, but a finer understanding of what Earth-like success may actually require. That is why the title Promise lands best not as a triumph, but as a clarification. JWST's verdict on TRAPPIST-1 is finally in, but the verdict is not that the dream came true, nor is it that the dream failed. The verdict is that the dream was too simple. The real system is harsher than the headlines once implied. The inner worlds look increasingly stripped or hostile. The outer worlds remain difficult and cold, more hidden than saved by distance. And the one planet that still matters most, TRAPPIST-1e, matters because it stands exactly where the real question lives. Not, is this another Earth? But, Can a rocky world around a red dwarf survive enough of its history to become climatically whole? That is a magnificent question. Harder than the one people first clicked for. Better too. Because if we ever do find life elsewhere, it will not be enough just to know where it is. We will want to know what kind of world carried it, what history allowed it, what thresholds were crossed and which ones were never triggered. We will want to know how the planet held together. Systems like TRAPPIST-1 are teaching us how to ask that in advance, how to read atmospheric survival, climatic continuity, and stellar pressure as part of one long planetary biography. In that sense, the system is already a gift, whatever the final atmospheric verdict on E turns out to be. It has given us a stricter imagination, a better grammar for habitability, a more adult relationship to hope. It has reminded us that the universe may be crowded with rocky planets while still being selective about worlds. It has shown us that a world can look promising from far away and still fail at the level where life actually needs it to succeed. And it has quietly returned us to Earth with altered eyes. That altered vision may be the final residue this story leaves behind. Not a single exoplanet glowing in certainty, but a changed sense of our own sky. Somewhere out there, around a small red dwarf, a compact family of rocky worlds circles through permanent days and endless nights, through heat and cold, through histories we are only beginning to infer from light. Some may be bare, some may be frozen in ways we do not yet fully grasp. One may still possess enough air, enough circulation, enough stubborn continuity to keep the question open. We do not yet know, but we know more than we did, much more, enough to understand that the difference between a planet and a world is one of the deepest differences in the cosmos, and enough to feel, perhaps a little more strongly than before, how astonishing it is that we live on one of the worlds that made it through. Made it through? That is the phrase that stays with me when I think about TRAPPIST-1 now, not because it sounds dramatic, but because it feels exact. A rocky planet does not become important merely by existing. It becomes important when it survives enough of the universe to remain capable of more. Enough atmosphere, enough internal heat, enough protection, enough balance between light and dark, enough continuity that chemistry is not endlessly reset, that water is not permanently exiled from usefulness, that a world can become one world instead of a set of disconnected extremes. Webb has not yet told us that TRAPPIST-1e made it through. It has told us something more disciplined, and in the long run, more valuable. It has told us which easy stories probably did not. It has told us that the inner planets are increasingly hard to imagine as anything but harsh outcomes. It has told us that the star itself must be taken seriously, not just as the source of warmth, but as a force that may have shaped every atmospheric fate in the system. And it has told us that if one world there still carries the possibility of climatic wholeness, that possibility is narrow enough now to matter. That is the real verdict. The age of easy optimism around TRAPPIST-1 is over. What replaces it is not despair, it is precision. A more demanding hope, a more mature kind of wonder. The kind that does not ask the universe to be simple in order to be beautiful. Because beauty was never the problem. We had that from the beginning. 7 rocky worlds around a small red star was always going to feel beautiful to us, if only because it stretched the old loneliness of the cosmos into something more crowded and intimate. But beauty without discipline is cheap. It evaporates at the first serious measurement. The beauty that survives Webb is different. It has passed through evidence. It has lost its soft edges. It has become harder, clearer, and much more difficult to fake. And that is why this system feels so alive in the mind, even now, even without a clean answer. Not alive in the biological sense, alive as a question, alive as a pressure on our assumptions, alive as a place where the universe has forced us to grow up a little in public. We wanted a nearby system of alternate Earths. Instead, we got something more useful, a compact map of planetary fates. Worlds too close to keep the air we hoped for. Worlds farther out, colder and more withheld, where distance solves one problem by creating another. And in the middle, one planet still holding the line between dismissal and confirmation, asking whether a rocky world under a red dwarf can keep enough of itself intact to remain climatically meaningful at all. If TRAPPIST-1e eventually proves airless, that will matter deeply. It will mean that even one of the most serious nearby habitable zone candidates around a small star failed to preserve the conditions we care about most. It will tell us something hard about red dwarfs, about atmospheric survival, about the cost of growing up too close to a star that spends too long being dangerous. It will make the galaxy feel, in one sense, less generous. But if E does hold a secondary atmosphere, if heat really is being moved, if water, in some form, remains part of a functioning planetary conversation there, then that will matter just as much. Not because it gives us a second Earth. It probably will not. It will matter because it proves survival is possible. Because somewhere in that compressed, difficult system, one world may have crossed enough thresholds to remain whole. Either answer is larger than one planet. Either answer reaches outward into the way we will read countless other worlds. That is what makes this such a profound moment in astronomy. We are no longer only discovering planets. We are learning how to judge whether they became worlds in the deeper sense, whether they carry air that matters, water that matters, time that matters, whether their stars left them enough peace, after all the violence, to become places where complexity could accumulate instead of merely endure. In that way, the search for life is becoming less romantic and more intimate, less about broad declarations and more about conditions, less about asking whether the universe is full of Earths, and more about asking how many rocky worlds ever really become habitable in the demanding, physical, connected sense that life requires. That is a harder question. It is also the one that was always waiting beneath the easier one. And perhaps that is why the story feels so complete, even before the final answer arrives. Because what has changed is not just our estimate of one system, it is our way of seeing. The night sky is not empty in the old way anymore, but it is not conveniently full either. It is full of thresholds, full of worlds that may have almost made it, or made it briefly, or never made it at all. Full of stars whose light gives and takes away. Full of climates we are only beginning to imagine honestly. Full of narrow survivals. Full of histories written in air, or in the loss of air. TRAPPIST-1 has become unforgettable because it gathers all of that into one place. A small red star, 7 rocky worlds, permanent day on one side, permanent night on the other. Atmospheres present or absent, heat carried or stranded, water exposed, hidden, frozen, or lost. A telescope listening across 40 light-years for the faintest sign that one of those worlds still has the thin moving skin that makes planetary continuity possible. And here we are, on our own world, able to listen. That may be the quietest and greatest wonder in the whole story. Not that the universe produced a system like TRAPPIST-1. It almost certainly produced many. Not even that one of its planets may yet prove climatically interesting. Greater than that, in a human sense, is the fact that matter on Earth organized itself into minds, built instruments, crossed the threshold from myth to measurement, and now sits beneath an ordinary sky asking whether another rocky world kept its air. That is an astonishing thing for a civilization to be able to do. It does not make us central. It does not make us wise enough yet. It certainly does not guarantee that the answers we most want will be the ones the universe gives. But it does mean something simple and immense. We have entered the era where worlds can begin to confess their conditions to us through light. TRAPPIST-1 has already confessed enough to change us. It has made us more careful with the word habitable. It has made us more suspicious of easy analogies. It has made Earth feel less like the default and more like a survivor. It has made the search for life feel less like a hunt for copies and more like a study of planetary endurance. It has taken one of the most hopeful systems in the sky and made it, somehow, both harsher and more meaningful. So no, Webb has not handed us a simple ending here. It has done something better. It has drawn the real outline of the question. It has shown us where the dream breaks, where it narrows, and where it still remains standing. And maybe that is enough for now. More than enough. Because somewhere around that dim red star, one world may still be holding on to the possibility of becoming more than rock. Somewhere in that compressed system, the line between planetary failure and planetary continuity may still be visible. Somewhere in the faint data still being argued over, the future of how we think about life around red dwarfs is already taking shape. We will keep listening. We should. But even tonight, before the last uncertainty closes, the deeper realization is already here. The universe is not asking whether we can imagine another Earth. It is asking whether we understand how rare it may be for a world to make it through. And under that question, beneath every spectrum and every silence, TRAPPIST-1 no longer feels like a promise. It feels like a verdict on how hard reality really is. And that, in its own severe and quiet way, is more wondrous than the easier dream ever was.